Objective 3.6, Operations with Functions. So in the second half of this chapter, we are looking at various ways in order to create new functions. So our parent functions are sort of the building blocks, the places that we start in order to make the functions that we need. And then there's different ways that we can create the new functions. So we've seen one way already, which is to be able to use the transformations, insert an a, h, or k value in order to be able to create something new. Another way is to actually do operations with functions. So we can actually add, subtract, multiply, and divide with the functions to create something new. Now our video is going to look a little bit different today because I want to be able to switch back and forth between PowerPoint slides and the image of the graphing calculator to kind of show you why things work the way they work. So our PowerPoint part of this is not going to be a full screen PowerPoint like it usually is, so that will allow me to be able to go back and forth between screens much easier. Okay, so let's see here. There we go. So our objective is to be able to perform operations with functions to create new functions by adding, subtracting, multiplying, and dividing, and then we want to be able to find the domain of the resulting function. We're not going to be too concerned about the range because that can get pretty difficult in these situations. So we're just interested in what the domain is going to be. So here's our first example. We want to be able to add and subtract functions, and we're going to start with an f of x function that is equal to negative 2x and a g of x function that is equal to x plus 3. Okay? Now, before we actually start with the whole domain and range and all of that, let's just see what that looks like graphically. So here we have our negative 2x. There we go. So here's our negative 2x, the blue one, and our red one is the x plus 3 line. Okay? Now, what we're talking about when we say we want to add these two functions is that at any given value of x, both of my functions give me an answer. So in my negative 2x function, when x is 0, y is 0. And in my x plus 3 function, when x is 0, y is 3. So when I say I want to take f of x plus g of x, what I'm really doing is adding the y values at that particular x. Okay, so especially if I'm saying f of 0 plus g of 0, that just means taking that answer plus that answer. And I can do that for any value along the way. I can pick any x value, and there's going to be a y here and a y here that I can add together. Even here, I have x and y. Even out here, even though I can't see it very well, I have to move the graph to see it, I have y's on both of those. Okay, so the idea is if I took all of those answers that I get by adding the y coordinates for each particular x coordinate, what kind of equation would I get from that? Okay, so we're going to go in here and we're going to say I want to take f1 of x plus f2 of x. And because I already have f1 and f2 defined, you can see here that it changed to a bold print, which means these are already defined functions. And now when I hit enter, you can see I get this new line here in red that is the result of taking y values of each of these x points and putting them together. Okay, let's get rid of this for right now. So this line right here represents the sum of my f and g function. Okay, so if we go back here now, if we look at the domain and range of each of these functions, because each of them are linear, and we can tell from our graph, both our domain and our range are going to be all real numbers. Okay, and if I do this algebraically, taking f of x plus g of x literally means taking the negative 2x, which is f, and adding the x plus 3, which is g, and ending up with negative x plus 3, which if I go back to my graph, you can see I have plus 3 for my y-intercept, I have negative 1 as my slope, and so yes, this graph really is negative x plus 3 as a line. Okay, and then to decide what the domain of this result is, we have to be a little bit careful. Yes, our result is linear. It seems like that should mean that our domain is going to be all real numbers, but we have to go a little deeper than just what it looks like. And we have to actually compare the domains of the functions that we started with. Now in this case, because both of the domains were all real numbers, it makes sense that our result is going to be all real numbers. But if these two domains differ, then we're going to have to decide what the proper domain should actually be. So in this case, it's pretty obvious. All real numbers for both means our result is going to be all real numbers. And that is because, going back here, when I did the trace, again, I could go anywhere for x and get the two different answers, right? And the two answers I get can be anything, right? We can go up, we can go down, it doesn't matter. Okay, so all real numbers will be the domain of my result. Now if I subtract, algebraically, that means that I'm going to take the f function of negative 2x minus the g function of x plus 3. I have to make sure I distribute the negative here to both of the terms in my second function, and I end up with negative 3x minus 3. So again, if we go back to this, and I go up here and I change this to subtraction instead of addition, we can see that we've got a negative 3 slope and we've got a negative 3 y-intercept. So it does make sense that that's our result. And again, notice that just because I'm subtracting my functions, that doesn't change the fact that my domain and range are still all real numbers. So I still have all real numbers for both domains, and my result is still going to be all real numbers. Because again, I can still get anything for x and get y values that go with it. I'm just subtracting those y values now instead of adding them. So I can use anything in my results, and my domain is going to be all real numbers. All right, now let's try something a little bit more complicated. So this time I have an f function of 3x and a g function of 4x to the 1/2 power, which we know now also is the same as saying 4 square root of x. So if I go over here and set that one up, I already have these set up in here, so I'm just going to turn these two off. There we go. And we'll turn on 3x and 4x to the 1/2 power. Okay, and then we'll turn off our combination there. All right. So again, you can see there's my f4 graph, which is the square root graph, and there's my linear. Okay, and again, if I did a trace here, we could see how there are certain values of x that give me a y value, and I can get the y value from both functions to either add or subtract. Okay? But what happens if I go down here? If I use an x value of, say, negative 0.6, what happens when I try to go to my other graph? Notice it says that's undefined because my purple graph here does not go less than 0. So if there's nothing from my other function to work with, to add or subtract to the y value from my linear, then I can't get any kind of result in that interval of values. Okay? So because of that, when we go to look at domain and range in our functions and in our result, our linear of 3x is still all real numbers for both domain and range. But now my domain for the square root is that x has to be greater than or equal to 0. And the range, the same thing. Y has to be greater than or equal to 0. That simply comes from what we were talking about in the parent functions. When I go to algebraically put these two together, taking the 3x plus the 4x to the 1/2 is just going to give me 3x plus 4x to the 1/2. There's nothing about those two terms that are in common, so I can't combine them. They're not like terms. I'm just going to leave it as the one plus the other. But when I go to establish the domain of this, I have to go with the most restrictive domain. They're not the same this time. One of my functions still uses all real numbers, but my other one only uses x values that are bigger than or equal to 0. And that's what we're seeing here. My purple graph here starts at 0 and goes to the right. So any x value that's going to be to the left in the negative region is not going to have another value in my square root function to add or subtract or multiply or whatever with. So that means the only values that I can actually work with are going to be values that are part of the square root function, which would also then be part of the linear function. So when you are looking at doing these algebraically, because you're probably not going to be graphing every one of these as you do your homework, so as you look at doing these algebraically, you need to decide what the domain of each function is individually, and then your domain for your results will be the most restrictive one of those two choices, because these are the values that are part of both functions, and therefore we can use them as x values in our result. Okay? Subtracting, same thing. It's still going to be the most restrictive, which is our x is greater than or equal to 0. So the nice thing about this is once you decide what your domain for your results should be for one operation like addition, it's going to be the same thing for subtraction. Subtracting the two functions doesn't change what our domains are and what we should use for a domain. It simply changes what we're doing with those y values to get our new results for our new function. Okay? All right, so why don't you pause the video for a moment and try to just do this algebraically. See if you can figure out what f of x plus g of x should be. See if you can figure out what f of x minus g of x should be, and then see if you can figure out what the domain should be for that result of the resulting sum or difference. Okay? Go ahead and pause your video for just a moment here, work those out, and come back when you're ready to check. All right, let's take a look at your answer. So because we are dealing with quadratics, x squared, 2x squared plus 5x minus 3, we know that the domain is going to be all real numbers for each of those. The range, I actually have made a mistake but because range is not something that we're interested in when we're doing these operations, it really doesn't matter right now that that's an error. We're just interested in the domain values. And since both functions have all real numbers for domain, we know that our result will have all real numbers for domain as well. So for adding, we're going to take x squared plus the 2x squared plus 5x minus 3, and that's going to give us the answer of 3x squared plus 5x minus 3 with a domain of all real numbers. For subtracting, we need to subtract the entire g function of 2x squared plus 5x minus 3. So that means the negative is going to be distributed to all three of these terms when we're simplifying. So that's going to actually give us a negative x squared minus 5x plus 3, and still with a domain of all real numbers. All right, so now let's take a look at multiplying and dividing with functions. Okay, so if I want to multiply f and g, divide it, and you notice here I have f as my numerator, g as my denominator, or the other way around, g over f. We want to be able to simplify that and also state the domain. So similar kind of thing. To multiply, we actually want to take our f of x function times our g of x function. So going back to our graphs here. So let's see, we were looking at negative 5x cubed. Let me turn these other ones off. Turn off that one and that one. So we have our negative 5x cubed and we have our x minus 1. So we can see here that we have a cubic and a linear. Okay, get rid of these labels so that it's not quite so messy. And again, if we did a trace, just move this up a little so we can see a bit more. If we do a trace here, we can again see how any particular x value is going to give us corresponding y values on both functions. And as I move x's, I still have corresponding y values on both functions. But now those y values are going to get multiplied. So if I take this negative 5 times that 0, I would expect my result to have a y value of 0 when x is equal to 1. If I come back here to when x is 0, I would be taking a negative 1 from the linear, but again times the 0 of the cubic, and so my result would also have an x-intercept here. If I go down a bit further, maybe something like negative 1.5, then I would have 16.9 times negative 2.5, and the result of that would be on my resulting graph. So let's actually see what that looks like. If we take, this was f5 of x times f6 of x, this is what we get. So again, you can see how we have our x-intercept right there because of taking the negative 1 from the line times the 0 from the cubic. That gave me a 0 on my result. I also have the x-intercept right there because again taking the number from my cubic times the 0 on my line gives me the 0. And then you can also tell things like my line here on the left of this x-intercept, my line is negative. My cubic is positive. So what happens when you take negative times a positive? You're going to get negative answers. So you can see the black graph here is down below the x-axis because my y values would be negative when I multiply the corresponding y's. Here in between the two x-intercepts, you can see that my line gave me negative y's, so did my cubic. So if I take the negative times the negative, my black ends up giving me positive results, And so that's why I have this little bump right here above the x-axis to show that I have positive results. And then again, if I go out here to the right of this x-intercept, I'm looking at positive y values from my line, but negative y values from my cubic, and so again we're going to get negative y values on our result. So when you're multiplying, it's nice because you can not only tell things like where intercepts are going to be, pretty much anywhere one of the graphs crosses the x-axis, that's where our result will also cross the x-axis. But you can also tell things like whether the graph will be above or below by looking at the kinds of answers our two functions gave us in the first place, positive and negative. Okay? But when it comes to the algebra of it, taking f of x times g of x still requires us to look at domain and range of each of our functions. So the domain and range of a cubic is going to be all real numbers for both. Similarly, the domain and range for a linear is going to be all real numbers for both. And my actual function for this black graph is going to be the function of taking negative 5x cubed times x minus 1. So my negative 5x cubed will be distributed, and I get negative 5x to the fourth plus, because the negative and negative will be plus a 5x cubed. This is the function, the equation for this graph in the black right here. Okay, and to tell the domain, we again compare the domains of the functions we're using, and since both of them are all real numbers, we're going to get a domain of all real numbers for our result, for our product. Okay. Now, what if we decide to divide? So if I want to take f of x over g of x, the setup is the same. I'm going to put my f of x function on top, which is negative 5x cubed. I'm going to put my g of x function in the denominator, which is x minus 1. And then I'm going to simplify anything that's possible. Now in this case, there are no common factors in the numerator and the denominator, so there's nothing to simplify. But when it comes to finding the domain, not only do I have to compare the two domains that I have here, but I also have to consider the fact that I have a variable in the denominator. And we know that with rational expressions like this, we cannot have a 0 in the denominator, which means I cannot use an x value that would ultimately make my denominator be equal to 0. So when you're trying to decide what your domain is going to be, you not only make the comparison here, but you also have to think about, is there any value that's going to make the denominator equal 0? And in this case, we can't use every single real number possible because an x of 1 is what will make the denominator 0. So we have to say the domain is everything except for 1, or you can just write x is not equal to 1. That implies everything else is possible for x, just not the 1. If we turn it around and put g of x in the numerator and f of x in our denominator, now what number is going to cause my denominator to be 0? Now it's an x value of 0. So again, everything else is going to work except for 0 because of what I now have in my denominator. Okay? And similarly, if we are looking at functions where domain is restricted, so for example, if I'm looking at an f of x to the 1/2, which is the square root of x, my domain is going to be x is greater than or equal to 0. My g domain is going to be all real numbers. So when I multiply this, I'm still just making the comparison, just like with adding and subtracting, and since there are no values of x less than 0 from this function, to combine with numbers in this function, I can't use those values. So again, I'm going to use the most restrictive domain And my domain for my result here is going to be x is greater than or equal to 0. I'm also going to use I'm also going to use the fact that because I have an x as a common base, I can add my exponents here, and so the 1/2 here plus the 3 there, which I changed to 6/2, that's going to give me 7/2. So 3x to the 7/2 is our simplified result, and the domain for that will be x is greater than or equal to 0. If I'm dividing, again, I want to be simplifying as much as possible, so I'm going to take the 1/2 minus the 6/2 that 3 would be equal to, which will give me 5/2 as the exponent on the x in the denominator. It's also going to cancel out the x in the numerator, so that's going to get replaced with 1. And now, because I have this possibility of a value that could make my denominator 0, I'm going to say, well, I still have to take this restricted domain, but now is there anything in that domain that could possibly make this 0? And you should always go back to the original setup before you simplified to make that decision. So in this original 3x cubed, what would be a value of x that would make that denominator 0? Well, the value would be 0. So now I go to my restricted domain and say, okay, was 0 part of this domain that I'm still working with? The answer is yes. X was greater than or equal to 0. So I have to take that 0 value out of the domain. And in this case, the way to do that is to simply say, okay, so x has to be greater than 0. I can't use the or equal to line here because I can't have x actually be equal to 0. Okay, so it's nice in that with adding, subtracting, and multiplying, once you find your domain for the two functions, it will be the same domain for all three results, whether you add, whether you subtract, or whether you multiply. The only twist that you have to be careful for is when you divide, you have to look for that additional potential problem of, are there any values that are going to make my denominator 0? And if so, you need to take that out of whatever domain you established in adding, subtracting, and multiplying to come up with a domain for dividing. If we flip it around and take a look at g of x over f of x, 0 is still going to be the value that's going to cause a problem there in my denominator, and so my domain is still going to be x is greater than 0. We take the 0 out, and this is what's left. All right, one more practice. Go ahead and take a look at these two functions. Think about what you would get if you multiply, if you divide f by g, and if you divide g by f, and state the domain for each one. Pause the video while you work on this and come back when you're ready to check. All right, so for multiplying, we would be taking 2x squared times 4x to the 1/3, which is going to give us 8x to the 7/3. Both quadratics and cube roots are going to have all real numbers for the domain, so we can use all real numbers for the domain of our product. And again, my range is a little bit wrong there, but because we don't care about range right now, we're not going to deal with that. For f over g, we would be taking 2x squared over 4x to the 1/3, which will end up being equal to 1/2 x to the 5/3 power. We still have all real numbers for both functions, but now we have this 4x to the 1/3 in the denominator, which means we cannot use 0. So we have to take that value of 0 out of the all real numbers for our final domain for this quotient. And similarly, if we turn it around to take g over f, now it's the 2x squared that's in the denominator. X equal to 0 is still the value that I cannot use, and so my domain is still that x is not equal to 0. Everything else will work because of my all real numbers up here. I just cannot use 0. All right, so I hope that gives you enough information that you can work on your practice problems in the 3.6 practice. If you have questions on this, because it's a bit of a strange lesson, it's not something we've dealt with before, so make sure you're finding the resources to help you with this, whether it's your textbook, whether it's other online videos or websites that might explain this a little bit more to you. If you need to send me an email, please feel free to do that. I'll try to get back to you as soon as I can. And don't forget to check your answers against the answers on Canvas to see that you're doing it correctly and that you're giving the answers that you should be giving. If you have any issues or questions, feel free to shoot me off an email and I'll answer you as quickly as I can. And that's it for 3.6. We'll see you next time.